Welcome, everybody, to our graduate statistics course, week 8. Can you believe we've done it this far? We've made it this far. Um, it's been for sure a challenging year, challenging semester for everybody in a variety of ways, I'm sure. For me, it's been a true challenge to deliver this course in this new format. And I really, truly hope that I'm compensating my lack of experience with online teaching with being responsive and trying to fix my mistakes as quickly as possible so as not to generate more frustration than is necessary um, for your learning and navigating this course. And again, I know it's been rough for some people more than others. And I want to restate my commitment to you and really believe that you don't have to do this alone. If things are getting hard, email us, contact us, just give us some time to help you, right? So start early in the week to work, give yourself time to work through the material. Everybody needs time to learn new concepts, new skills, and building that resilience to the discomfort that that we feel when we don't know something that you know it's things are not making sense for a while, and building resilience to that feeling is truly fundamental, I believe, for your success in a career in the career path that you end up choosing, right? Because that's what will make you a life learner. And that's what the market really wants right now, that we're ready to learn new things. We're ready to feel that discomfort that comes with pushing our boundaries, just stepping outside of our comfort zone. And this is what I think you should take grad stats to be. Even if you're never going to be a data analyst, take this course and this experience as the, the, the motivation for you to do, to navigate the discomfort of stepping out of your comfort zone and learning programming, something that you never encountered before, needed to do before, and learning new concepts in statistics, so on and so forth. So take it as that, if nothing else, that you're experiencing the discomfort of pushing boundaries of what you know, right, already, and expanding it to a new place. And then I'm sure at the end you feel pretty powerful that you survived this, and you will survive this if you dedicate the time that is required for learning, right? So you need to put the time in, and we'll put the time in to match your time and be by your side, walking with you. All right. Okay, I'm also very glad to hear multiple people saying that you're communicating with each other and you're building community in this course, helping each other out. That is great. If you are one of the people that are navigating this course with more ease, reach out to your colleagues, see if they need help. Maybe hearing from your perspective as a new learner will help them navigate the course with more confidence. So reach out, be active about this if you're not struggling. If you are one of the people that are struggling, again, learn to ask for help. It's no shame to ask for help. It is a necessary thing to succeed when we are, again, trying to learn something that's challenging to us. And not being scared of being in that situation and asking for help is, again, great practice. So please practice that. Ask for the support you need to succeed. All right? Let's talk about last class. So lots of stuff we've learned. So it's probably been a challenging class, perhaps the most challenging class of all, because we're bringing together a bunch of building blocks from previous classes, bringing everything together to then formally test hypothesis that we're interested in. So the first concept that we introduced to you was the concept of confidence interval. And that's a pretty important concept in statistics because it allows us to estimate with a level, with a desired level of confidence, a particular parameter of the population. One example we worked with is our intention to estimate. We had a question about the IQ of mothers of gifted children. We wanted to know if that was higher, if the average IQ of mothers of, and we used the example, the question that we had was about for instance, the IQ of mothers of gifted children. We wanted to know if their average IQ is higher than the average IQ of the general population. So remember, there is a true average IQ when we take the IQ of that we could find if we took the IQ, if we measure the IQ of all mothers of gifted children. So that's the population of interest. There is a true average IQ. The thing is that why I can't have access to all of the mothers of gifted children. So with research, what do? We take a random sample from that population and we try to estimate that true average that exists, that's a true value, true parameter, the mu IQ, right? Now, if I needed to get 1 point estimate, the best one would be taking the average IQ of my sample. But taking the average, getting this point estimate of this true parameter, which is the average IQ of mothers of gifted children in the population, the chance of us getting it precisely right is very low, because it's like the fishing in murky water idea, using that stick. If we try a bunch of times to get the fish, we'll only be precise and get a fish a few of the times, right? Same, if I were to sample from the population of mothers of gifted children a bunch of times and estimate the mean every time, the mean will vary, will not be the actual mean of the population a lot of the times. It will be close, but it will not be precisely that a lot of the times. And that's the sampling error, right? Now, if I use a confidence interval, it would be more like throwing a net to try and catch the fish, right? The confidence interval I compute from my sample data, and it's like a net that I throw to catch the true average of the population. And if I get multiple samples and I throw that net, I compute that confidence interval every time the confidence interval will be slightly different. But if I compute a confidence interval with 95% confidence, it means that if I compute that interval 100 times, I'll get the mean inside of there. I'll get the fish 95 times, right? If I compute a 90% confidence interval, meaning imagine I were to take 100 samples from the population and compute the confidence interval 100 times. If it's a 90% confidence interval, I'll probably catch the true average 90 times, about 90 times. So that's what it means to say that the confidence interval, we're 90% confidence that confidence interval includes the true mean of the population. So it is an important concept. And it provides us with a quick and dirty way to test hypotheses. Why? Because if I compute the confidence interval of my sample of mothers of gifted children, and it does not include the value of IQ, the average IQ of the general population in there, that suggests that it's not a very typical value, right? It's not a typical value for the population of mothers of gifted children, which means it's likely not the same. The IQ of mothers of gifted children is likely not the same as the typical population. But again, that strategy does not give me the probability of observing that particular average IQ that I observed in my sample if I were to sample multiple times from the population, right? So the idea is, can we construct a sampling distribution of IQ means, let's say, under the null hypothesis that 100 is the center of that distribution, and then compute what's the likelihood of observing the IQ of mothers of gifted children that I observed in my sample. And if that probability is low, less than 0.05, I say, yay, I will reject the null hypothesis that the average IQ of mothers of gifted children is just like the IQ of matters in the general population, in favor of the alternative hypothesis, right? So the Z-test was used in this case, in the case of our example in class, because we met the conditions to apply the central limit theorem to construct the sampling distribution from the data of one sample only. So we are not running the experiment a gazillion times to construct the sampling distribution of mean IQ. We're not doing that under the null hypothesis. We're taking the data from one sample. And because certain conditions are met, independence of observations, and either you have a very large data set, above 30, or you have a not very highly skewed distribution, then you can assume that the sampling distribution is going to be normal. So it's the Z distribution because that's the standardized normal distribution. And you can put the center to be equal to the expected mean under the null hypothesis. And the sampling variation, the expected sampling variation, can be computed from the standard deviation of the sample, right? You just have to adjust by the size of that sample. So standard deviation divided by the square root of n. That's the variation that's expected if you were to sample multiple times. So because the sampling distribution of the mean is normal, we can define it in a standard form, which is a Z distribution with mean 0 and standard deviation of 1. We can then compute a Z statistic that will tell us how far is the estimated mean in my sample from the mean under the null hypothesis. In the case of the IQ example, the mean under the null is 100. The mean of matters with of gifted children was, 118. And it turned out to be a bunch of standard deviations above the mean. So very, very rare to observe. It would be very, very rare to observe that kind of mean, that large mean under the hypothesis if the population of matters of gifted children were really just the same as the general population in terms of IQ. It would be very rare to see that average. So we then dismiss the null hypothesis in favor of the alternative. So this is the process of testing hypothesis, right? So we did that with the Z-test. And before we move on to our next adventure, I need to tell you that I did a little shifting with the schedule, the class schedule, because I was planning on doing some categorical data analysis before moving on to numerical data analysis. But I thought continuing on with numerical would make better contact with what we've seen before. So in this class, we're going to review the Z-test and then understand what the conditions are that would require the use of the Z-test to test hypothesis about differences in mean. And then we'll continue to see what if one of these conditions are not met? What is my alternative? And then I'll present you the t-test as the alternative. So I think it will be a smoother ride from Z-tests, which tests hypothesis about the mean, when we can apply the central limit theorem, and then move on to the t-test, which is continuing to allow us to test hypothesis about differences in mean, but when the central limit theorem conditions are not fully met, which requires that we use a different distribution, not the Z distribution, but the T distribution in order to test hypothesis and compute our confidence interval. So we'll see that this class. So this class will focus on, again, hypothesis tests about differences in mean. And we'll do that under conditions that does not allow us to apply the central limit theorem. And we will instead use t-tests and construct the t distribution and use t-tests to test hypothesis. All right, so see you then. And please watch all of the videos before you move on to the lab. All right, see you then. Bye.